So the next speaker now is Jasper Halekas. So the Lunar VERTEX mission, a landed investigation on Reiner Gamma, again, a very enigmatic feature. So please, Jasper, go ahead.
Thank you very much. Good morning. Yeah, so I'm going to tell you about the Lunar VERTEX mission. This is a mission which is already selected and in formulation. We just passed our preliminary design review about a month ago, and we hope to launch in a little under 2 years if all goes well. So to give you a little bit of general background about what we're doing, I think that most people know that the moon has magnetic fields. Not a global magnetic field like the Earth, but small inhomogeneous patches of magnetized crust around the surface. We don't exactly know what controls this distribution of magnetic field that we see. The most likely origin for these features is magnetization in an ancient dynamo, but how and why we see the inhomogeneous distribution that we see now is not at all clear. You can measure these fields with orbit. This map that you see here is made of measurements from orbit, but you can't completely characterize these fields from orbit because they're very, very inhomogeneous. The few times that we've taken a magnetometer to the surface of the moon and moved it around, you see the magnetic field go from north to south to left to right over scales of a kilometer. So if those places are representative, then these fields are very, very inhomogeneous indeed. Despite their small scale, though, they seem to have significant interactions with the ambient plasma environment. So a number of spacecraft, set of international missions have made measurements which show that these magnetic anomalies, although small scale and inhomogeneous, can actually affect the plasma environment around them. And it appears that they can shield a portion of the surface from the incidence of the solar wind plasma. And you see some measurements here on the right. This is a map of solar wind reflection. And the black contours there are the magnetic fields again, and the red color is showing you that a large percentage of the solar wind is reflected over these magnetic anomalies. You're seeing the big magnetic anomalies on the far side here, but you see that even some of these small magnetic anomalies reflect the solar wind. And you can see the same thing in energetic neutral atoms here in this picture in the bottom. Now, there's another interesting thing about these magnetic anomaly regions, and that is the fact that a lot of them are correlated with markings on the surface. These markings are usually called swirls for obvious reasons. They're high reflectance markings, and they tend to be kind of sinuous and, to use a technical term, swirly. Wherever these swirls occur, they're found to correlate with strong magnetic anomalies. Not every magnetic anomaly has a swirl, but every swirl, as far as we can tell, has a magnetic anomaly. So however these swirls form, it seems that they must have something to do with the magnetic fields. A number of different origin scenarios have been proposed. One is that ancient cometary impacts created both the swirls and the magnetic anomalies. There are a class of theories that have to do with some kind of dust motion in magnetic and or electric fields around these things. There's another class of theory that has to do with the properties of the surface and the structure of the surface regolith being altered in these regions. And then perhaps the simplest theory, but by no means accepted, is that these are simply regions where the surface has been shielded from the blast of the solar wind over millions and billions of years. And it's like a photographic negative. Those regions of the surface have not been exposed as much as their surroundings. Now, people who study space weathering don't all agree that this would work out because, of course, you'll still have micrometeorite weathering. And so there's a lot of controversy still about what creates these swirl features. Because of all these mysteries and controversies, these regions are kind of a natural laboratory which allow us to study a variety of different physics topics. One is just sort of the geological aspect of these, the magnetization. How does the crust get magnetized? What is the structure of magnetization? If we look up close, can we distinguish between some of the origin scenarios for this magnetization that we see in the rocks? The other side of the coin is the space plasma side of things. Can we understand how these magnetic fields, even though they're so small scale, actually form little regions that are shielded from the solar wind? What kind of fluxes of charged particles still reach the surface? Are they completely deflected or just decelerated, et cetera, et cetera? And then there's the space weathering aspect. Can we understand what has happened to create these strange spectral features on the surface? What space weathering processes are responsible for weathering the surface inside and outside of the swirl regions? So we think that these regions are a really cool place to study, and it's kind of the intersection of a bunch of different fields. And because of that intersection, we named our mission Lunar VERTEX to represent that intersection of multiple different fields. So to get into the science goals, we have three main science goals, which are sort of the three things that I've talked about so far. One is to investigate the origin of lunar magnetic anomalies, understand how the magnetization got there. Two is to investigate the origin of these spectral features, the lunar swirls that we see. Three is to determine the structure of the mini magnetosphere that forms over Reiner Gamma. Along with those three top-level science goals, we get a couple of bonus things. One is that we have a really perfect experiment here to evaluate the importance of micrometeoroid weathering versus solar wind weathering. Because in the strong magnetic field region, we think we turn off the solar wind source, micrometeoroids are still there. So what differences does that cause in the weathering of the surface? We'll be able to make that measurement conclusively. And finally, by measuring the environment near the surface, we'll be able to provide input to strategic knowledge gaps for human exploration. So how do we do this? Well, part of our investigation is on a lander. So we have three investigations on the lander, three instruments. One of those is the VERTEX camera array. So we'll be taking pictures to survey the landing site geology and do photometric modeling of the regolith characteristics. We have a magnetometer, or really a magnetometer suite, because we're mounted on a lander here, which is not necessarily magnetically clean. We actually have a science magnetometer, and then we have 4 magnetometers mounted closer to the rover to allow us to subtract off any fields of the rover itself and get a clean measurement of the magnetic field of just the moon itself. Then we have a plasma spectrometer, which measures both ions and electrons over a broad field of view to characterize the plasma that reaches the surface in these interesting regions. And we'll compare that to measurements from the Themis Artemis probes in orbit to understand, what's the input and then how much of that makes it through the magnetic field to reach the surface. Now, a key feature of our investigation, and I think probably the reason that we got selected, is that we also have a small rover. This rover allows us to get away from the region of the surface which is contaminated by the landing, and it also allows us to go across the swirl and compare a dark part of the swirl to a bright part of the swirl and see how they're different. So to do this, we have a small lander from Lunar Outpost, which is a really cool little guy. It is semi-autonomous, so we can basically tell it, okay, drive to this next point, and it can do that semi-autonomously. As we're going along our traverse, we will, of course, be stopping and making measurements frequently. And the measurements that we're going to be making are made by 2 little instruments. One of them is another magnetometer, which is basically a copy of the lander magnetometer system. So we're going to measure the structure of the magnetic field and how that varies spatially across the swirl. And then the other is a little multispectral microscope, which basically illuminates the surface with LEDs and gives us composition and texture information underneath the rover as we drive along. So this is really important because, again, we can compare the properties of the surface in a dark lane and in a lighter region of the swirl. We're delivered to the surface as part of This payload carried by Intuitive Machines. So we're just one of the investigations that is carried on this lander. There are several others from an international host of providers. So Intuitive Machines builds this beautiful lander for us, and then we get integrated to it. You can see some of our investigations on here. Here's the plasma spectrometer here, and you can see the booms up on top where the magnetometer will be, and so forth. The rover gets dropped out of the bottom here and drives off after we land, etc. The landing site, we've tentatively picked the landing site that you see here. So we'll basically start.
Jasper, 2 minutes left.
Thank you. Yeah, so we'll start in a bright area of the Reiner Gamma swirl region, and then we'll make a traverse toward the dark lane. So the highest priority is to get into one of these bright swirl regions, and so that's why we start there. But then we want to compare the properties of the light and dark parts of the swirl, see how their magnetic fields differ, and see how the spectral characteristics of the surface differ. And so we have a traverse that you see here, which allows us to cover those different regions of the swirl. The team is led by Dave Blewett at Johns Hopkins Applied Physics Laboratory. I'm the deputy PI. Most of our management and engineering team is at APL, and then we have instruments from a variety of other institutions. We also have a small science team. That science team includes notably Lon Hood, who is the first one who discovered the magnetic field at Reiner Gamma. So it's exciting to have him on the mission and sort of providing that connectivity back to the original discovery of Reiner Gamma. Here's just a summary walk-off slide. I won't read this, but I'll mention again that we just passed our preliminary design review, which is our one NASA review. So we're moving forward and we're fabricating instruments. The lander is, following its own path, but they're moving forward on their side. And then we marry our suite to the lander. And if schedule holds, we will launch and we'll have a 1 lunar day mission in early 2024. Thank you very much.
Okay, thank you very much, Jasper. Just on time, so we have time for 2 free questions. And at least I don't see in the chat something, but in the meantime, could you go back to what you expect for your rover in terms of trafficability? How much distance could you cover?
Yeah, so we're looking to cover at least 100 meters. If things go really well, that might be up to a kilometer. But the minimum is kind of 100 meters to get away from the zone that's most disturbed by the lander and to allow us to sample both bright and dark parts of the swirl.
Yeah, okay. That is the key question. What happens?
Yeah, absolutely.
Okay, so I don't know, do we have more questions in the chat? Can you plan simultaneous lander and orbital B measurements to correct for the wind?
Yeah, that's a really good question. So as long as something really horrible doesn't happen, there are 2 Themis Artemis probes in lunar orbit, which are still healthy and still have plenty of resources and everything, and so still should be operating in 2 years from now. And so using those 2 spacecraft, we can measure the magnetic field and also the incident solar wind plasma in lunar orbit. And we can use that to, subtract out the solar wind component and get just the crustal magnetic field, which I think is the thrust of this question. But we can also use that to quantitatively evaluate how well these magnetic anomalies actually shield the surface by measuring the solar wind flux up high and then seeing what actually comes down to the surface where we're measuring.
Hey, this would be terrific indeed. Yeah, thank you.